go back to the top of the slide. Where I stop and I turn and I go for a ride till I get to...
Right, so that was a well-known Beatles song called Helter Skelter. And what on earth has that got to do with conservation of energy? And the answer is that a Helter Skelter is a fairground ride which absolutely embodies and depends on the whole idea of conservation of energy. And to see, we don't have a Helter Skelter in Bhutan. The nearest thing we've got to it is here in Centenary Park to look at the nearest thing to a Helter Skelter. And so one of the things you might say is, why in a children's park? Well, the message I want you to understand is physics isn't difficult. Physics is child's play. Sanjit is now going up and stopping. He has gone up. He has increased his gravitational potential energy. Up there, he's got more potential energy than he had when he was down here. So he's got potential energy. Now, Sanjit is going to turn that potential energy into kinetic energy. Are you ready, Sanjit? Go!
Ah!
The potential energy he got going up the stairs, gaining potential energy through height, mgh, he's going to turn into kinetic energy, a half mv squared. Go!
Ah!
And that is all you need to know about the principle of conservation of energy. He got potential energy using his muscles and what he had for breakfast as the source of energy, and he's turned it into kinetic energy. mgh, a half mv squared. Physics is child's play. Now, we came to Centenary Park because I was hoping to show you another transfer of energy from potential energy to kinetic energy in a swing. When you go up, you've got potential energy, and you can come down, whoosh, you've got kinetic energy, movement energy, gravitational potential energy, movement energy. Unfortunately, the swings are broken, they don't work, and some of the slides are broken too. Such a pity. If any viewer or parent is interested, they could give a little money perhaps to renew the slides and the swings in this lovely little children's park. But also because I wanted to show you another transforming of potential energy to kinetic energy in a children's swing, where when the swing is up there, you've got potential energy, and then it turns into movement energy, kinetic energy at the bottom, and then back again to potential energy. But unfortunately, the swings here in the Centenary Park are broken, they've gone. And I'm told that if you actually want to take your child for a swing, you have to go to Gaza. And here's a picture of some real swings working in Gaza. So wouldn't it be really wonderful if some generous citizens helped to restore some of the children's activities here in this lovely setting? They all need a bit of renovation and a bit of maintenance. However, let's look at some other examples of helter skelters. So in a helter skelter, you get in a sort of a truck which is on rails, and you are lifted right up into the sky, and there's the truck sitting on the rails. Inside that truck is you, and it comes up to the top having been pulled up by a chain, and then it's allowed to go like that. And I'll do that again. You're up in the sky. You've got gravitational potential energy, mgh, where h is the height above the ground, m is the mass of the truck plus you, and g is the acceleration due to gravity. Now, you may know that as 9.8 meters per second. We'll call it 10. So there you are. You've got gravitational potential energy because you're up high, and then suddenly you go, whoops, Let's try again. Holding it steady, Roshan. Here's you in the truck. You've got gravitational potential energy, and to your horror, you come to this big drop. 1, 2, 3. When the track was like that and went horizontal on the bottom, all the potential energy was turned into kinetic energy, and by Newton's first law, if Roshan were not in the way, the ball would keep on moving along there forever and ever. But what about this situation? Lift the end up, Roshan. Now, I'm going to release the ball. It's got some potential energy because it's above the ground. Watch what the ball does. You know what the ball does. Up. And what did the ball do then? What the ball did then was its gravitational potential energy turned into kinetic energy when it was at the bottom, but then it rose up again, and the kinetic energy at the bottom turned into gravitational potential energy again. Now, conservation of energy tells us that energy cannot be created or destroyed. It can only turn from one form into another. The gravitational potential energy turns into kinetic energy, which then turns into potential energy again. And if we cannot lose any, then the ball should return to the same height as I let it off. If I let it off 1 meter above the ground, it should go up until it's 1 meter above the ground. That shows conservation of energy. Unfortunately, some of the energy is used creating heat as friction on the ball. So the ball does not return 1 meter high, it returns something less. And then gradually all the energy is gone. But it hasn't gone. What has happened to the energy? It is turned to heat energy. Energy cannot be created or destroyed. It can only be turned from one form into another, and in this we're turning gravitational potential energy into kinetic energy. And then in the end, because of friction between the ball and the track, all that original gravitational potential energy has ended up as heat energy. No kinetic energy there. It's all gone as heat energy, and it's heated up the atmosphere and contributed to global warming. Now, another example of turning potential energy into kinetic energy. There's a marble, a glass marble, and it's above the ground, 2 meters above the ground. The mass of that is 100 grams, 0.1 of a kilogram, 1/10 of a kilogram. So 0.1 kilograms, 2 meters above the ground, and g, the acceleration due to gravity, we'll call 10 meters a second squared. So it's got gravitational potential energy, mass times gravity times the height. And when it falls down, that gravitational potential energy turns to kinetic energy just before it hits the ground. And then when it hits the ground, some of it will produce potential energy again, and the ball will bounce up, but some will go to create sound, you can hear it hitting the ground, and to create heat. So there we are, gravitational potential energy turning into kinetic energy. A bit comes back as potential energy, but a lot goes off in sound and heat. Tell me, what's this marble made of? Watch it. That was glass. Most of the energy that it had up here has ended up as heat and sound. Watch this one. Is this rubber or glass? Whoops. When the rubber one bounces, most of its potential energy comes back again as potential energy. Goes from potential, kinetic, and then back to potential, just like rolling up the slide. You can calculate easily how much energy goes off as heat and sound if we look at this 2 meters high and now see how high it goes. It comes there. So there was 2 meters, it's come back about there. So if you work out that height there and do mgh, that's the potential energy that it's lost. It's not lost it, that's turned to heat and sound when it bounced. And if you've got a really good rubber ball, you might get it to come back up to there. But you will never, ever get it to bounce higher than where you let it go. If I let it go from 2 meters, it will never get higher than 2 meters. Because if it did, it would have had to gain some energy from somewhere. And energy is not created, it's not destroyed. It cannot get back higher than where it was let off from. And there's a very good experiment or demonstration to show that, and I'm going to get Roshan to volunteer for what I would call a near-death experiment. Right, so we've left the children's playground now because we're going to do a death-defying experiment in a minute. Well, now, here is a swing, or you could call it a pendulum. There's a big heavy stone at the bottom on the end of a rope, and I can give it potential energy by lifting the stone to here, and the stone has got gravitational potential energy because it's high up. When I release the stone, the gravitational potential energy all turns to kinetic energy of movement, and then it'll, with luck, bang into the wood and it'll be lost as sound and heat, and a little bit will come back. Let's just try that. So I've given it potential energy by doing work to lift it up, and now I'm going to let go. And it hits the wood. If I lift it a bit higher, it'll hit the wood harder. Are we ready? And it hits the wood. Now, it's not much fun having a piece of wood there, so let's put a person there. Out of the way, Karma. Let's put a person here. And let's give it a bit more potential energy by lifting it higher up. So, Roshan, move back a bit and put that just underneath your jaw, a bit, yeah, just underneath your jaw there. Now, I do hope it's not going to break your jaw, but I want you to stand there. Don't move, be brave. When I say go, just let go of the rock. Oh dear, now, the hospital is only just down the road. Are you ready? Go. Ah, well done. You notice that it came up to about here. Now, he was very brave just standing there, because if it had gone to there, it would have broken his jaw. How did he know that he was safe? He knew he was safe because you can rely on physics. Physics gives you certainty. The rock had potential energy there. It cannot get more than it started off with. So it cannot go higher, because that would have meant somebody had to give it energy on the way. If Roshan had pushed the rock down, and I'm going to give it a push and you're going to go out of the way. If he had pushed it down, then it would have gone a bit higher and it would have broken his jaw. But he's given it potential energy, he's not giving it a push, so it cannot get back higher than it started out. And in fact, due to energy lost in the rope and air resistance, it will come back lower. Let go now. And it came back just to about there. And if we measure the distance from there to there, think of it, mg times that h, that is the amount of energy which has been lost due to air friction and friction in the rope. But the energy isn't lost, it's converted to heat. Because there is a very funny thing about energy. All energy, no matter what sort, electrical, mechanical, gravitational potential, nuclear, all energy, electrical energy, it all ends up in the end as heat energy. It all ends up as heat energy. Now, remember the lessons. Potential energy turns to kinetic energy, turns back to potential energy. You can't get more energy than you started off with. The energy is conserved. That is to say, you cannot make more energy, you do not get less energy. But energy is turned into different forms. So the potential energy there is turned into kinetic, back into potential, back into kinetic, and back into potential. But some of the original potential energy has gone in friction, air friction, and friction in the rope, which has turned to heat energy. So conservation of energy. And if by dropping a ball you are invited to prove the law of conservation of energy, you won't do it, because some of the energy will get changed to heat and sound. So your measurements will not prove the law of conservation of energy. In fact, there is a very interesting physics principle. A great scientific philosopher called Karl Popper, he wrote a wonderful book in which he showed that you can never prove anything, you can only disprove it. Because if you carried out 1,000,000 experiments to prove Ohm's law, the 1,000,001th experiment could always show that it was wrong. So you can never prove anything. All you can do is carry out an experiment to disprove something. So if ever you're asked to describe an experiment to prove the conservation of energy, you need to be very careful. So this can be a pendulum, or as I say, it could be a swing. You could imagine a child sitting on the end of here swinging. But it's also the basis of a wonderful and exciting fairground ride. There is a swing, and we'll show you a video of it in a moment, and it's built right on the edge of a great big canyon, on the edge of a cliff. So the edge of the cliff is here, so when you're out here, you're actually looking down 1,000-foot drop. And so when you swing, if you can imagine yourself on this swing, as you go out, now down below you out there is a deep, deep canyon, and you think you're going to drop into it, but you don't. Here's a little video to show it.
This source of adrenaline is located on a cliff edge 1,300 feet above the Colorado River. The swing holds 4 passengers and dangles them at 112 degrees above the horizon at a speed of 50 miles per hour. From the highest point, you can see almost an infinite crevice below. The creator of the swing, Steve Beckley, only tried it once and was so frightened that he didn't dare to ride it again. And before you hop on the swing, you have to sign a disclaimer saying that this attraction can lead to falling, traumas, and even death. Can you believe it? Children and teens under 18 are only allowed with this paper signed by their parents.
If I bring it up here, it was at the ground level, and I have lifted it up. And let us say I lifted up 1.5 meters. So the height above ground is 1.5 meters. I then release it, and as it goes past his feet, it's moving, kinetic energy, and then it comes back to me here, but not quite so high because of loss of energy due to heat, air resistance and things. So let's do a calculation which will ask the question, how much kinetic energy has it got now, and how fast is it moving now? Here's Roshan holding the pendulum, and I've lifted it up so that it is now 1.5 meters above the ground. So H is equal to 1.5 meters. The stone had a mass of 2 kilograms. So M equals 2 kilograms. And little g, the acceleration due to gravity, we'll call 10 meters per second squared. In school you may call it 9.18, which makes for very complicated calculations. So I'm just going to call it approximately 10. There's just one little point here. The mass is 2 kg. Don't mix up the g in kilograms, kg, with little g, the acceleration due to gravity. That isn't the acceleration due to gravity, it's just a short way of writing kilograms. Sometimes people mix those two up. So, we're talking about potential energy turning into kinetic energy. The potential energy here, kinetic energy there. So, potential to kinetic. You must know and learn off by heart the formula for potential energy is mgh. And you must know and learn off by heart the formula for kinetic energy, a half mv squared. The potential energy turns into kinetic energy. So mgh should equal a half mv squared, assuming there is no loss of energy due to friction of the air and friction in the rope. So let's assume there's no air and that the rope is frictionless. So mgh equals half mv squared. Now, there's something really useful about this, because you notice m is on both sides of the equation, because instead of turning into, we can just say equals. M is on both sides of the equation. Therefore, very conveniently, you can cancel it out. It doesn't matter what the mass is. It could be a 10-ton iron ball, or it could be a 10-gram piece of my cake. So this makes the formula much easier, because we simply get gh equals a half v squared. So if we want to calculate v squared, the velocity when it's at the bottom, that's much easier. We can now bring the 2 up there, so we get 2gh equals v squared. In other words, v equals the square root of 2gh. Now, that equals the square root of 2 times little g, 10, times h, which is 1.5 meters. So, v, the velocity of the stone when it passes Roshan's feet, is root 2 times 10 is 20, or let's do it another way around. 10 times 1.5 is 15, so that's 2 times 15 equals root 30. And Roshan has got his pocket calculator already to tell me that the square root of 30 is 5.477. Well, we don't want 3 decimal places, so let's just make that 5.5 velocity meters per second. So the stone is going along there at 5.5 meters a second. So we can easily work out the kinetic energy, because, kinetic energy equals a half mv squared, which equals a half m, the mass of the stone was 2 kg, and v squared is, what's v squared? Answer, 30, which equals a half of 2 is 1, so that is 1 times 30, which equals 30. So it's kinetic energy. What units do you measure energy in? Joules. So that's 30 joules. And that should equal the potential energy it had here, and potential energy is mgh, so that's 2 times 10 times 1.5, which equals 2 tens is 20 times 1.5, answer 30 joules. So the kinetic energy it had is the same as the potential energy it had in the beginning. Two formulas you have to remember, there and there. Try a similar problem for yourselves. And I'll just do one more problem about shooting an arrow up into the air. And remember what I said in earlier programs, never let arithmetic, mathematics, calculus make physics seem difficult, because physics is child's play. And the next calculation I'm going to do, it's not child's play, it's father's play. Because let's think about this. There's the ground. There's Dasho. And what has he got in his hand? A bow. And he fires an arrow straight up into the air, and it comes straight down again. A person fired the arrow straight up into the air, and as it turned around and started to come down, I thought, oh dear. Fortunately, there was a little bit of wind, and so instead of the arrow coming straight down, the arrow came down and landed just there. But what a good job there was a little bit of wind. So don't ever try this with a bow and arrow. But let us imagine a situation where you've got Dasho with the bow, and alongside him you've got Roshan with a stopwatch, and he starts the stopwatch when the arrow is released. It goes up, turns round, comes down again, and he stops the stopwatch when it hits the ground. And the stopwatch reads 4 seconds. So the time to go up and down was 4 seconds. So how long did it take to go up? Well, to go up, it will have taken half that time, 2 seconds. So it took 2 seconds to go up. Now, what is making it stop and turn round? Answer, gravity. So we have to think about little g, the acceleration due to gravity, which is actually deceleration in this case. And you may remember from learning your equations about uniform motion that d, the distance travelled, equals a half times the acceleration times the square of the time. You should have learnt that somewhere else. And if you're thinking of something going up in the air, the acceleration is a deceleration, and it is little g. So the distance that it goes up is equal to a half times g times the square of the time that it took to get to the top. So therefore, how high did the arrow go? It went a half times little g times. Now remember, 4 seconds to go up and down, so 2 seconds just to go up, so t is 2, t squared is 2 times 2, so that equals a half times 10 times 4, and a half of 10 is equal to 5 times 4 equals 20. And that is d, the distance the arrow rose. So answer 20 meters. That's how high the arrow went. And I hope my calculations are all correct. You notice I've chosen numbers to make the calculations easy. In exams, the examiners often choose difficult numbers to make the calculation difficult. But that doesn't make the physics difficult. It just makes the arithmetic difficult. So the arrow went up 20 meters. How much gravitational potential energy did it get? Well, GPE, gravitational potential energy, equals mgh. I hope you can read my writing. That's meant to be m. mgh. So the mass is 1/20th kgs, multiplied by acceleration due to gravity, 10, multiplied by the height it went, 20 meters. So 1/20 times 10 times 20, the two 20s cancel out, very easy. So the answer is 10, and it's gravitational potential energy. What do we measure energy in? We measure it in joules. So it gained 10 joules of gravitational potential energy. Okay, so it got 10 joules of gravitational potential energy. Where did that come from? It came from firing the arrow, and when you let go of the arrow, it had what sort of energy? It had kinetic energy. So the movement energy of the arrow has turned into gravitational potential. So how much kinetic energy was there? How much kinetic energy? Well, there'll be 10 joules of kinetic energy, because assuming no loss due to air friction, the amount of kinetic energy must equal the amount of gravitational potential energy that it got, conservation of energy. So if the kinetic energy was 10 joules, we can work out how fast was the arrow going when it left the bow. How fast was the arrow going when it left the bow? And we do that quite simply. 10 equals kinetic energy, a half times the mass of the arrow. Well, we said the mass of the arrow was about 50 grams, which is a 20th of a kilogram. So 1/20th, half m times v squared. We don't know. We're trying to find the velocity of the arrow. So 1/40 times v squared is equal to 10. 10 joules is equal to 1/40 times v squared. So therefore, move the 40 over there. 40 times 10 is 400 equals v squared. So therefore 20 is equal to v. So how fast was the arrow going when it left the bow? Answer, it was going at 20 meters a second. Well, let me just summarize what you need to know and understand. First of all, you need to understand that energy isn't created, energy isn't destroyed. All that happens to energy, it is turned from one sort to another, from one form of energy to another. It's converted. It's just like money. You've got 1,000 nultrums. You can turn it into US dollars. You can turn it into Thai baht. You can turn US dollars back into nultrums. Money can be converted from one sort to another, but it doesn't just disappear, and it doesn't suddenly come in. If you stand here, you suddenly don't find you've got 10,000 nultrums in your pocket from nowhere. So energy is a bit like money, and I go into that a little bit more in one of my Royal tutorial programs. Secondly, there are two formulas you need to remember from this lesson. The formula for gravitational potential energy, mgh, and the formula for kinetic energy, a half mv squared. And if you're turning one into the other, you simply put those two equations equal to each other. And so remember, physics is simple. It's child's play. Don't let the calculations make it complicated for you. Try to understand the basics. And remember the Beatles song we began with about a helter-skelter, this lovely, terrifying fairground ride. We'd like to end with Mr. Bean on a helter-skelter.